Hi everybody, it's Mrs. Harbin and we're talking about molecular polarity in this video notes. Here's what you can do already. Draw Lewis dot diagrams from atoms, ions, and compounds. And we could tell their shape, but now we're going to be able to tell their molecular polarity. Okay, we have to know the difference between a polar bond and a polar molecule and be able to look at a molecule and use the type of bond and the molecular shape to figure out its polarity. Okay, so there's not much to look at in the book on this topic, so I'm going to challenge you to find an internet source to give examples of polar and nonpolar molecules and explain what it means. So, hey, look, it's a bear. Okay, now you know why I'm playing the bear song right there. Lyle love it, gotta love him. So, polar bonds means, let's look at the part. So, carbon's got electronegativity of 2.5, fluorine's 4.0. So, what's the diff? 1.5. All right. So if the difference is 1.5, that means this is a polar bond. So how do you figure that out? You subtract electronegativity. Once you know the difference in them and find out it's a polar bond, you could draw a dipole arrow pointing to the more electronegative one, and you could put a partial negative charge and a partial positive charge on those atoms in that bond. Okay, that's looking at a bond. But when we want to know if a molecule is polar or not, we have to look at the bonds and then the shape. Okay, so we know that the difference between hydrogen and oxygen is 2.1, 3.5. What's the diff? 1.4. So HO bonds are polar. The oxygen's more electronegative, so we can draw the arrowhead pointing to the oxygen. So up here we have partial negative, down here at the bottom we have partial positive. And so this is the whole molecule, and the thing that helps us decide is the shape. All right, because this is an angle, so it's angular or bent. Then those polar bonds don't cancel out, and so this is going to be a polar molecule. So a polar part doesn't always mean a polar whole. So you could have polar bonds and not a polar molecule, and we'll see. But you could have polar bonds and a polar molecule. Wow, let's see what we're looking for. If you want to know if you have a polar molecule, first you need polar bonds. Once you know you have polar bonds, you look at the shape of the molecule, and if the polarity of those bonds doesn't cancel out, then you have a polar molecule. If you have a nonpolar molecule, either two cases for that. There are no polar bonds, no dipole arrows, no polarity at all. That means a nonpolar molecule. Or there are polar bonds, but they cancel out. So you need to see some examples. So is the molecule polar? Okay, there's a yes answer or a no answer, but let's look. So first you look at the bonds and find out if they're polar. Then if you have polar bonds, you look at the shape to see if those polar bonds cancel. In water, it's an angular shape. In an angular shape, the bonds cannot cancel each other out because it's like a hill. An angle is like a hill. The top of the hill is going to have a different charge than the bottom. So one, polar bonds, check. Okay. Two, angular shape. Polar bonds don't cancel in an angle. So then if polar bonds don't cancel, then polar molecule. All right, so step one, check the bonds. Hey, C and H make a nonpolar bond. So those are three nonpolar bonds. This molecule would be a tetrahedral, okay? So remember the wedge comes at you, filled in, dash wedge goes behind. These are in the plane of the molecule, the plane of the paper. These three bonds are nonpolar, but here we have a polar bond. So here's our dipole arrow, partial negative on the chlorine because it's got the higher electronegativity, partial positive on the carbon. This one polar bond in a molecule means, so polar covalent bond, that's why we drew the arrow. One arrow means polar molecule, All right, molecule is polar, okay. All right. Oh, look. One bond, one arrow. HCl is polar. Okay, polar bond. Polar covalent bond, PCB. One arrow means polar molecule. All right, so you're probably saying, all right, I get the polar thing. What do you mean about the nonpolar? Well, let's look. Between carbon and oxygen, this is a polar bond because carbon has electronegativity of 2.5, oxygen is 3.5, so this is 1.0. What's the diff? 1.0. So there's an arrow pointing that way for polarity of that bond, an arrow pointing equal but opposite direction for the polarity of that bond. Together, that linear shape of two opposite but equal poles. Means that outside here is the negative, inside here is the positive. The positive and the negative center meet at the same spot. So this is a nonpolar molecule. Nonpolar molecule. Okay. First we check that we have polar covalent bonds, and we do. The CO bond is polar, but it's a nonpolar molecule because those polar covalent bond cancels. So we check the polarity of that bond as polar covalent bonds. We draw our dipole arrows. This molecule is a tetrahedral. Tetrahedral. A tetrahedral, if you notice, all of these on the outside have negative charge. The carbon in the middle has a kind of positive charge, partial positive. So if you look at all of those, where the center of the negatives is here, the positive is here. So there's no opposite sides on the molecule. It's either negative it's negative all around. So even though there are polar covalent bonds, it's tetrahedral. So we have to know the shape. And a tetrahedral, this tetrahedral is a nonpolar molecule because those bonds cancel. All right, so here's some examples of polar molecules. Here's nonpolar molecules. Got any more? Oh, sure I do. Okay, a polar molecule, a molecule is polar if there's one dipole arrow in it. Okay, then it's going to be polar. This molecule is polar because it's got a negative end up here and a kind of positive end there, and nothing cancels that out. This molecule is one bond. One polar bond in a molecule means polar molecule. Okay, polar bond, no, doesn't cancel, doesn't cancel. So that equals polar molecule. So some linear molecules can be polar if there's only one bond in them. This is a trigonal pyramidal molecule. Okay, so let's check the bonds. First, an NH bond is polar because the difference between N and H is 3.0, it's 0.9. All right, and so then arrow point to the top of the hill, to the top of the hill, to the top of the hill. So if you think of a pyramid, all right, up here's the top of the hill of that pyramid. Okay, this is going to be a negative part of the hill, that's going to be positive, so this is a polar bonds. Polar bonds don't cancel, so this is a polar molecule. All right, again, those are polar. Maybe you get that. But what does it mean to be nonpolar? Okay, so we have a tetrahedral. Again, we have polar bonds between C and Cl, but those four polar bonds in this tetrahedral cancel each other out. So this is a nonpolar molecule. Because the polar bonds cancel. Molecule. All right. This is a trigonal or trigonal planar. Okay. So even if these are polar bonds, okay, the polarity of the bonds goes in equal but opposite directions, makes a flat triangle. Flat triangle, kind of positive on the outside. Oh wait, kind of negative on the outside. That's where the arrows are pointing, kind of positive in the middle of that triangle. So this is a nonpolar molecule and another nonpolar molecule. Any more examples? All right, so here's the main idea you should think of. Polarity of molecules means that the polarity of the bonds don't cancel, so it's polar, or the polarity of the bonds cancels, and then it's nonpolar. The other kind of nonpolar would be if there's no polar bonds at all. All right, so a bond is polar if the end is between, when I say end, it would be between 0.5 and 1.9. Okay, if the end is between 0.5 and 1.9, that makes the bond polar. Okay, the end is the electronegativity difference. A molecule is polar if the bond is polar and the shape does not cancel that polarity. So here's a bunch more. Okay, NH3. So here's your N, here's your H's. This is a trigonopyramidal. Trigonopyramidals are going to be polar if the bonds are polar. If bonds are polar. Why? Because the top of the hill is going to be different than the bottom of the hill. Tetrahedral. Tetrahedral. Well, first of all, CH4 is a 2.5 and a 2.1 is 0.4 non-polar covalent bond. So you'd go over here and do nothing. Don't draw any arrows on a non-polar bond. So this is non-polar bonds. So this is a nonpolar molecule. Okay, so tetrahedral will be, this would have been nonpolar if that was nonpolar bonds, but they are polar bonds. Okay, but a tetrahedral is going to be nonpolar, especially if it's nonpolar bonds. Okay, PF5, this is trigonal, 5 areas of electrons, bipyramidal. And why is it bipyramidal? Because you have a triangle in the middle, so that's your trigonal. Then you have a pyramid at the top and a pyramid at the bottom. Polar or nonpolar? Well, if these bonds are polar, okay, so this is 2.1, this is 4.0, so it's 2.9, right? Nope, it's 1.9. Got that, all right? 1.9 is polar bonds. Polar bonds pointing to the fluorines. You draw those on there, draw that on there. These are all partially negative on the outside. All right, but there's no one side that's different than the other, so this is going to be a nonpolar molecule. Hey, look, it's SF4, all right? SF4 has our funny seesaw shape, okay? Sulfur and fluorine is 2.5 and 4.0, so it's 1.5. What's the diff? Polar bond, polar bond. Arrows, 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 all right? So these are all kind of negative by the fluorines. Kind of negative, that's a partial negative. And partial positive at the top of this hill here. Even though those two cancel, the hill doesn't cancel, so it's a polar molecule. Alright, moving on. Let's see the next one. Oh, look, it's water again. Water is angular, okay? Angular, and the polar bonds are pointing to oxygen, away from hydrogen, partial negative, partial positive, polar. Polar bonds, polar molecule. BRF5. This is a square pyramid. Okay, square pyramid. So the square pyramid is going to be polar. Why? Because the difference in electronegativity is 1.2. So this is Br and these are all Fs. All right. So up here, you have the arrow that doesn't cancel. All these arrows cancel. Equal but opposite, equal but opposite, equal but opposite. But then you got this one arrow that doesn't cancel. So up here you got kind of negative. Down here kind of positive. So that's going to be polar. CH3Cl. So here's our C. We'll put these as H's. And this will be our Cl. Alright. So a CH bond is nonpolar, no arrows. But a CCl bond is polar. Okay. Because there's a difference of 0.5. So we got kind of negative here, kind of positive. There's nothing to cancel that arrow, so it's a polar molecule. Alright, ALF3. Alright, ignore the fact that aluminum and fluorine would probably make an ionic bond because the difference is 2.5. What's the diff? 2.5, that says ionic. But we'll ignore that for now and say if this was the aluminum and this were the fluorine. Alright, pulling that way, pulling that way, pulling that way. But this is a trigonal planar, a flat triangle. A flat triangle, alright, all around the outside you got negative, negative, negative. There's no top of the hill, there's no bottom of the hill, that's different. So this is nonpolar. Okay. Arrows cancel, nonpolar. Alright, so what's the deal with this? Well, the next one we'll talk about it again. But polar molecules love water. Why? Water's polar. Water is polar. If anybody asks you, is water polar? You better say yes. Water is polar. So polar things will dissolve in water because they're also polar. But nonpolar things won't. This is going to be a nonpolar molecule. Alright, it's got H's on the outside. It's a tetrahedral. These are nonpolar bonds. This is a nonpolar molecule, but this is polar. Okay. Polar things love water. Oh, look at the polar bears in water. Oh, polar bears are soluble in water. Polar things are soluble in water. Okay, like I said, the book doesn't have the bear song. Book not good, so good with is a molecule polar or not. So find a source. Can you draw loose dot diagrams? Can you tell their shape? And now, can you tell their molecular polarity? You need to know polar bonds, polar molecules, and the shape. Alright? Peace out.